11 is about the geometric application of integrals, or in other words, how to use integrals to compute properties related to geometric forms or objects. Okay, so we're going to see how to compute areas of figures, volumes of figures, and also some lengths as well. Okay, so we'll start with the area of flat figures. Okay, something like this, areas in 2 dimensions. And so we can imagine a form given by this, right? How to say, the borders defined by 2 different functions g and f, right? So it's pretty straightforward to see if you realize what the integral of g from a to b is doing and the integral of f from a to b is doing, is that the area of this form S is just the integral between a and b of g minus f. That's the function, right? That's the value of that area, right? And that's going to give us a positive value actually, right? But the thing is that this is not general, because sometimes we have a function g like this and f like this that cross over, okay? And we want this, the area of this form, or did you want these 2 areas, right? So what we want to do is actually find the intersection, it's the point where f and g intersect, so that here we want, this is f here, right? And this is g. So what we want here is the integral between a and this point of intersection of f minus g, and here is this integral between this point and b of g minus f, right? So we can write this in a general way like this: a of this form S, right, is the integral between a and b of the absolute value of g minus x or f minus g, it doesn't matter, right? And so in order to compute this in actual examples, right, this is the formula that we're going to use. In order to compute this, we need to find where the these absolute values are going to be positive or negative, right? I mean the argument inside. Okay, so for instance, as an example, let's compute the area between this function f, which is x times x minus 2, and g, which is x over 2, right? So now this is a parabola, right? This is doing something like this, and g is doing something like this, right? So between the interval 0 and 2, right? Well, actually, what's going on here? This parabola, right, is a positive parabola that does something like this. Between 0 and 2 is negative, right? And then this x over 2 is something like this, right? So this is the area that we want, sorry, this area, not to here, right? This is 2, this is 0. This is the area that we want. So here it's obvious that g is greater than f for all this interval between 0 and 2. So what we want is the area of this form S, right? S is the integral between 0 and 2 of x over 2 minus x times x minus 2, right? And well, we can expand this. This is x squared minus x squared plus 2x, right? This is what we have. And so the integral of this is obviously x squared over 4 minus x cubed over 3 plus x squared. And all this we have to evaluate between 2 and 0. So you have 2 squared over 4, 1 minus 8 thirds plus 4. And then at 0, all of this is 0. So we have 1, this is 3 thirds minus 8 thirds is minus 5 thirds plus 12 thirds is 7 thirds. That's the area of that particular figure. Okay, and then let's do another example where there is an actual intersection. Okay, for instance, we have this function f is x and g is x cubed over 4 in the interval minus 1, 2. Okay, so in this interval we have that x is doing this is f, and let's see, at minus 1 this is doing something like this, right? This is like this, and this is like this. So between -1 and 2, let's see, we have this and this, right? Let me first prove this, right? This is the area that we want. This is -1, this is 2. How do I know this? Well, let's see where these two functions are equal, right? So where is x equal to x cubed over 4 or equal to 4x, right? So this is equivalent to x cubed minus 4x equals 0, which is equivalent to x times x squared minus 4. So the solutions of these are x at 0 and then x equal plus minus 2, right? So these are the 3 points of intersection, right? So between -1 and 0, we have the g, right? As this the cubic polynomial is greater than f, and between 0 and 2, f is greater than t. Okay, so we have the area of this function is between -1, the integral between -1 and 2 of the absolute value of g minus f. What we know, because we have evaluated those, is that this is, we can separate in two integrals between -1 at 0 of x cubed over 4 minus x dx, which is greater than 0, and then plus the integral between 0 and 2 of x minus x cubed over 4. Okay, and so here this is going to be x to the 4 over 16 minus x squared over 2 evaluated at 0 and -1, and then plus the integral, let me put some brackets here, the x squared over 2 minus x to the 4 over 16. Okay, and again now evaluated at 2 and 0. Okay, so this is at 0, this is 0, and then we have -1 is let's see, is 1 to the 4 is 16, right? So this is -1 over 16, sorry, and then minus plus 1/2, and then we have plus 4 over 2 minus 2 to the 4 is 16 over 16, 1, and then at 0, 0. So this 2 minus 1, 1 plus 3 over 2 is 16. So this is 48 over 16 minus 1 is 40. Wait a minute. No, yes, sorry. So this is 2 minus 1 is 1 plus 1/2 is 3/2, which is equal to 24 over 16. Minus 1 is 23 over 16. Okay. Now, in some cases, we're gonna see figures like this, okay, or maybe figures like this that are not easy to parameterize as functions of y and x, maybe because they are going to have more than one value for y or not. So in these cases, what we do is we, or in some cases what we have already is a function, is a curve given as a function of two variables, which is first is r, okay, which is the distance from the origin, right? This is r, which is, and then we have theta, which is the angle of the function, the point with respect to the x-axis. Okay, so we have this point, right? So we have this Cartesian coordinates, right? Then we can rewrite this point x, y as the same point in what we call polar coordinates. Okay, so these polar coordinates are the distance from this point to the origin, right? So this is r, and you know, using Pythagoras theorem, it's easy to see that if this is y and this is x, then r is just the square root of x squared plus y squared, right? And then this is theta. This is the angle that this point, this vector if you want, makes with the x-axis, right? And so theta is going to be the arctangent of over theta, or sorry, over x, right? In many cases we're not going to use this formula to compute this, right? But you see how this goes. This is theta is the angle that has as a tangent the value of y over x, right? That's how you use this. Okay, but don't worry too much about this, because in many cases you're not going to have to use this formula to. You just have to think your way through, and that way you can get the polar coordinates from the Cartesian coordinates. Okay. So and the other way around, that's how you go from Cartesian to polar. How do you go from polar to Cartesian? Well, it's easy to see from here that x is going to be r times the cosine of theta, and y is equal to r times the sine of theta. Okay, so that's how you go from one to the other type of coordinates, right? Now, how do we, if we are given a curve in polar coordinates, right, how do we find the area of that curve, right? Well, the idea here is, instead of using this rectangle scheme that Riemann used, we're going to use this circular sectors. Okay, so instead of covering the x-axis, what we're covering is the theta axis, if you want, right? We're going over all the possible angles that our form covers, right? And so we're going to partition the angles, the interval of angles into a different set of intervals, such that in each interval we have a circular section. Okay, so we have our partition of theta, which starts at theta 0, theta 1, blah blah blah, and then theta n, right? Whereas theta 0 is a and theta n is b, right? And then in each of these intervals, right, we have circular sectors of area. The area of the circular sector is the angle, the area of any given circular sector, like this, right? Okay, something like this. The area of this is given by the angle that is covered in the circular sector times r squared. Okay, so if you think about the circle, right, this is divided by 2, right? So what's the area of the circle? We have pi times r squared. What's the angle of this circular sector? It's 2 pi, right? So it's 2 pi divided by 2 times r squared. That's the area of the circle, right? So if you think about the getting circular sectors, for instance, a quadrant, right? It's obviously a fourth of the whole area, right? So it's just all of this divided by 4. So it's just a kind of a proportionality constant, right? How much of the circle of this is, it's this angle. Okay, that's how you get this. Okay, so how do we write then? So this is the area of the circular sectors. Then we have what we can approximate as the lower sums and the upper sum, just like when we did with the rectangles in the last unit, right? And for the Riemann sum, so we have the lower sum is going to be the sum, right, from the first interval to the nth interval of 1/2, and then the minimum value of this radius in this interval. So this is mi squared, right? This is the radius squared. That's the formula of the area of the circular sector, and then times the angle. But the angle is just theta sub I minus theta sub I minus 1, right? This is what we had done for our Riemann sums, right? And this is going to be smaller than the area of this form. And then again we have the upper sum, which is 1/2 of the maximum value of the function here, right? This is mi squared, and then again times the angle, right, which is the difference between the two values of the partition, right? So this is equivalent to this definition of the integral by Riemann if function f, right, which is given by this, which is a function of theta, right? So we have a function of theta such that it has a maximum, is the maximum, or if you want the supremum of f in this interval, right? In this where theta is between theta I minus 1 theta I, and the same with the minimum, right? Just so you theta I minus 1 theta I of f theta. Okay, so that's the function in terms of theta. Then what we need to do, if you realize that the integral of this, if it exists, it's going to be the integral between a and b, where we called a and b the initial and end angles, of 1/2 of f of theta squared, which is what the function that we're going to integrate, right? D theta. So this is the area of surface that is given to us in polar coordinates. Okay, let's use that in an example. Okay, well, let's go next. So we have this figure. Okay, this is one of those in which if you see using the definition of the integral with if this is given in Cartesian coordinates, so the curve is given by this equation: x squared plus y squared cube is equal to y squared, right? This is the curve. Now, doing the integral of this in Cartesian coordinates seems hard enough, because this is going to be, you have to, in order to get you have to solve for y here in order to get an explicit formula here, right? So you're not going to be able to do it easily. Well, what we can do is we can transform this into polar coordinates. Okay, so remember that x squared plus y squared was equal to r squared, so this is r squared to the cube, so this is r to the 6, and y squared, y was r times the sine of x, so this is r squared times the sine squared of theta. Okay, in other words, this is r to the 4 equals sine squared of theta. In other words, r is equal to the square root of the absolute value of the sine of theta, right? So if you divide this, you have 2/4 in the exponent 1/2, right? So this is our f of theta that we want to integrate over, and theta can be any value between 0 and 2 pi, right? Because you start here and then you do the round around the circle. Yeah. So now, how do we compute this integral? Well, we have the area of S is, remember, 1/2 of the integral between 0 and 2 pi of f of theta squared, which is the sine of the absolute value of the sine of theta, right? Now, the absolute value of the sine of theta is the sine of theta when 0, let me write this like this. This is between 0 and pi, this is the sine of theta, right? And then between pi and 2 pi, the sign is negative, so this is going to be minus 1/2 of the sine of theta between pi and 2 pi. But it turns out that the sine of theta between pi and 2 pi is minus this, so this is actually, well, you can see here that this is 2 times this integral, right? You can do this algebraically, or you can see it geometrically. So this is 2 times this integral, okay? This integral between 0 and pi of the sine of pi d theta. The integral of the sine is minus the cosine between pi and 0. Minus 1, minus 1, minus 2, minus that, 2. Okay? And that is the area of this form, right? That is given to us. We can write in polar coordinates.